I'm Andres. I work for Citus Data, and most of my time is spent developing Postgres. And I'm a PostgreSQL committer, and yeah, that's enough about me. What I want to talk today about is tunable durability. So for that, we first have to define what is actually durability. And it's the D in ACID. So you might have heard about ACID, the properties of a relational database management system. And what means the D? What does the D in there mean? To quote Wikipedia, the durability property ensures that once a transaction has been committed, it will remain so even in the event of a power loss, crash, or other errors. So basically it means that if you wrote something and you got back as a result, hey, the write succeeded, the commit of the transaction succeeded, the data will not be lost afterwards. And for some of the work you're doing, that might be very important because you cannot tolerate like random data loss. But there are other types of writes where you might not necessarily need that. And that's where the tunable comes in. And I'm trying to talk a bit about two definitions of the tunable bit. One of them is how can we make the cost of crash safety a bit lower? And the other part is how can we choose which level of durability do we want today for the specific use case to make the costs acceptable and to give enough guarantees for whatever we are doing. So to understand how all this works, we have to go a little bit into detail about how does Postgres and how do most relational database systems and a lot of other type of data stores actually guarantee crash safety, because that will have effects on both performance and understanding how performance is impacted by durability and how you can reduce the cost of it. Basically, the trick that allows to have crash safety is so-called ValLogging. And what that means, or redo logging, or journaling, that's all the names for the same thing. What basically means that if you do a write to the database, say you execute a begin statement, what that does, it doesn't write to the data table directly to where the actual data is stored. Instead, it writes to a so-called journal. In that journal, it just writes something like, I'm inserting data at block so-and-so of that table. And then it writes in there. And after that, it goes to the shared buffer, the buffer cache, which is where Postgres has its in-memory copy of the data, and modifies the data there. But it doesn't have to write that data out to disk. It's fine to be there in memory. And then it does the next modification. It might, for example, the next modification might be, for example, creating an index, updating the index to reference that the row we just inserted. Or it might be, for example, it might be a commit that says the transaction that was in progress right now is now committed. And all these individual inserts into the sequential log, which just gets larger and larger, are so-called records. And these records can contain mostly arbitrary data. And what this log then is used for is that if we have started to write to the data and we just continue writing and the log gets bigger and bigger, then at some point we might, for example, crash. And after we crashed, what this log is used for, then after the crash, Postgres gets to the beginning of this log and just redoes everything in this log. Which means, like, if it says we are inserting something to rows so-and-so of that table, then it redoes the insert. And after that, we can be sure that the data is updated after the crash. And it will do so for everything that happened until the crash, where it knows that all that data has been written to disk. And it knows that because this write-ahead log it has checksums on it. It has some other it uses a C or C checksum. It has some other cross checks so we know that it's looks valid. And after we played all the records up to where we crashed, we can continue accepting new writes. In Postgres, the write-ahead log is not one huge file that gets larger and larger. Instead of broken down into 16 megabyte chunks, but most of the time you don't notice it. You will potentially have seen those 16 megabyte files, which are 16 megabytes by default. You can recompile Postgres to use different sizes. if you set up like val archiving, if you have set up like a archive command, a restore command, the files that are handled there, those are the val files, and those are the 16 megabytes chunk of this stream of data. So after we've recovered all the data, we can now start accepting data, writes again, and so the log will grow and grow again. But you might get the point that if we just ever append to this endless log of actions, then we'll have the problem that this log will get as large as all your writes you've ever done, which is obviously a problem. You can't have that. It would also be the other problem with that, besides disk space, would be that if you crashed, you would have to replay everything since the beginning of your database. And if your database has like several terabytes of writes a day, that would not be fun. So every now and then, the database does something called a checkpoint. And at the checkpoint, it will go through all the buffers it has a memory of the data and write it out to the disk. And that means like it has to check all the buffers of the data. And after that, it will call fsync on all the files that have been written out. Fsync is a file system call that says to the operating system, make sure that this file that I've written to is now safely on disk. And the operating system will first write out its own cache, and then it will tell the disk, hey, disk, you're not allowed to do any caching of the writes that have previously been happened. And after that, you can be reasonably sure that the data has been written out. There have been a number of disks that lied about fsyncs actually working for the name of performance, because if you don't actually write data reliably to disk, it will appear to be faster. But on the other hand, if you crash, you might lose data. So these days, most of the vendors actually have working fsync, or it's not an fsync on the disk level, but the equivalent. So after we have performed this checkpoint, which can take a while, we can now, because we've done one previously here, we can now delete all the val files that we don't need anymore. And we have now got rid of all the old data, and then we can continue writing. In Postgres, the checkpoint can happen actually while you continue to accept writes, which is obviously important for performance, because if you imagine you have shared buffers set to like 500 gigabytes, and you wanted to not accept writes during all the writing out all these 512 gigabytes of data, that would not be good for availability. So we accept writes during this. But you can also imagine that checkpoints, because they have to potentially write out all this much data and have to call fsync on all the files, can be very expensive operations. It can be a very expensive operation. So tuning of checkpoints is one of the first things you often have to do if you have to optimize for write performance. So how are these checkpoints triggered? The most important parameter for that is checkpoint timeout. By default, Postgres will just perform a checkpoint every 5 minutes, and unless some other things happen. And in many cases, it can be a good idea to increase the time, or decrease the frequency of checkpoints, increase the timeout, because then you'll less frequently do these checkpoints which write out all the data. And if all your work fits into shared buffers, if all your writes can normally fit into shared buffers, you might otherwise not write out any data to the disk file in normal operation. So increasing checkpoint timeout can have a tremendous performance impact, because your total amount of writes to the disk can decrease. The other thing is that the parameter called checkpoint segments, or since 9.5, it's called max val size. And that's basically the size, not if you write too many of these files between a checkpoint and another checkpoint, your disk space might get exceeded. So Postgres, whenever checkpoint segments is exceeded, or max val size in newer releases is exceeded, we perform a checkpoint to avoid too much log being collected. And the default in release before 9.5 was 3, which is like 48 megabytes, which is obviously 48 megabytes of writes that usually in a busy database will happen sometimes within less than a second. So if you run a write-heavy database, you'll definitely need to increase this parameter. And even in newer releases, the default now is 1 gigabyte, and it's configured a bit differently. That's still not a whole lot, because here max val size does not just mean the space needed between one and the next checkpoint, but it also needs like this space here and potentially some space that we also allocate additionally. So this usually means that after every 512 megabytes of writes, of write-ahead log writes will trigger a checkpoint. In a busy database, that's not enough. So you might need to tune this. And if you enable logging of checkpoints, which is the log checkpoints parameter, then you will see something like log checkpoint starting by time, and that's when this checkpoint starts because of time. Or you might see something like log checkpoint starting xlog, and that's if you're exceeding checkpoint segments max val size, and that's usually a sign that you want to increase checkpoint segments. But there's a trade-off here. I'll come to that in a second. And the other cases are a bit less interesting. If you shut down the database and you don't do it with kill 9 or something, then the database will perform a checkpoint so it doesn't have to do crash recovery after a restart. And then it will just say checkpoint starting. It does so because of a shutdown, and the immediate means that it'll try to do so as fast as possible. And you also can do manually issue a checkpoint and then it tries to do a checkpoint whenever you say so. That's in practice. There's some cases where you want to do that, but it's not that frequent. So, as I said, the log checkpoints parameter will tell you how much, what happens at a checkpoint. It will tell you how long did it take, how much write did it perform. So that's a very crucial parameter, unless you run a database that's basically not doing anything and is basically just sitting there. You should always enable this. And one of the things to compute, to understand the impact of a checkpoint, and those are really, in a lot of databases, that are the most heavy operation that you'll see operationally, is that the maximum amount of writes a checkpoint will perform is shared buffers. Because, as I said, a checkpoint what a checkpoint does, it will go once through all the buffers and write them out to disk. And if it can't write more than there's buffers, so the maximum amount of writes it will do is shared buffers. But it also will only write out buffers that actually have been marked as dirty. So if you actually don't update any data in shared buffers, if you have a read-only workload, it will also not write anything, with some notable exceptions. But the next thing is that Postgres can do so-called checkpoint spreading. And that's if you can set checkpoint completion target to a number between 0 and 1. And that will mean that it will try to take longer for a checkpoint, because to avoid a checkpoint happening as fast as possible would probably overload your I/O system, because it would potentially write 100 gigabytes of data within a second. Obviously, your storage is not going to be able to do that, or most of your storages are not going to be able to do that. So checkpoint completion target, which defaults to 0.5, means that it will try to delay the checkpoint completion over checkpoint timeout. So if you set it to 0.5, it will try to delay the completion of the checkpoint for 2.5 minutes and spread the writes evenly out over that period of time. So then that allows you to calculate that the maximum number of writes approximately per second is that shared buffers divided by timeout times target. And that's roughly the write rate you're going to have from checkpoints. And you might also guess that because the checkpoint completion default target is 0.5, by increasing it to 0.9, for example, which is it nearly takes as long as checkpoint completion, checkpoint timeout, you will spread the same amount of writes, because the maximum is still the same, it's still maximum shared buffers, over a longer amount of time. So in a lot of cases, it can be a good idea to increase checkpoint completion target. The other thing to consider is if you increase checkpoint segments, that means that after checkpoint segments, that after a crash, you'll potentially have to do more crash recovery, because there's more write-ahead log data between two checkpoints. And that can take time. If you have 100 gigabyte of val and you do crash and you need to recover that, that will not take a half a second. Depending on how good your system is, that might take 3 minutes or something. And depending on your availability criteria, that might not be acceptable. So the recovery time is something that influences how large you can set checkpoint segments. In my experience, you can do between 3 and 10 segments of shared buffer, like val segments per second on good hardware, but it really depends on what kind of I/O patterns you have. If all your writes are random writes over a large amount of data, then you might get less. If all your writes are sequentially appending to a table that doesn't have any indexes, then you probably can do more. So it's hard to be very precise about this, unfortunately. Another thing that's very interesting to know about is that Postgres has to do so-called full-page writes. What full-page writes are that the first time that Postgres writes to a table, to a page in an index, in a table, in nearly everywhere, it has to do so-called full-page write, which means it will write out not just the change to the page or the table out into the write ahead log. It will include a full copy of the entire page, and that's because during sometimes the hardware can lose, like, only write half a page and then crash. That's so-called, but the other part is the old version of the page, and that we can't have that. That's why we have to include the full page in after a checkpoint if you modify an existing page. And those can be very large. If you have very frequent checkpoints and you have random workloads, I've seen cases where 98% of the writes were full page writes. And that can be bad from a performance and from a space usage point of view. There's a tool since 9.3 or 9.4, I think, pgxlog-stats, which can compute how much full page writes you're doing. And there's two ways to reduce full page writes. The first is to just have less checkpoints, because we only have to perform these full page writes the first time after a checkpoint. The other is to enable compression of the write ahead log, which is a parameter called val compression, and that exists since 9.5. And if you enable it, the volume of write ahead log can often reduce drastically, but it will also use more CPU because we now have to perform compression. So this is basically.
Is it possible to target the logs onto a specialized hardware like NVRAM or like some kind of a flash-based device, specifically just the log?
Yes, you can symlink basically the pg_xlog directory while the service shut down, please, to wherever you want to do, and then the writes will happen there.
The other question is that, like, when you talk about the copy on write, which is being done, like the whole page write is that's being done.
Mm-hmm.
If you have any kind of an SSD device, like, you want to do the full page write and keep accumulating the writes over time, and then finally write it back with respect to page boundary, rather than updating just maybe 1 byte inside an 8K.
That one I'm not quite clear about. It sounds like a bigger topic. Can we do that one just a couple minutes afterwards? So far I've talked about basically how can you make the write ahead log, the durability cheaper, or how can you tune your Postgres installation towards this. And one of the good remarks here is, like, sometimes it can make a lot of sense to redirect the write ahead log to a separate device, which is like faster for that kind of workload, but potentially smaller. You might not be able to fit your whole multi-terabyte database on it, but a couple 100 gigabytes of write ahead log might be okay. But the other side of what I meant about tuning is that you can tune what kind of level of durability you want to have for your database and for your writes. And the default there is that the default writes, which are durable writes, to know whether they are too expensive or too cheap for you, you have to know what they actually cost. So basically, to understand the cost of doing like a durable transaction is at the minimum that at the end of a transaction we have to flush this write ahead log to disk, and that means we have to do a write of the write ahead log up to this point, and then call fsync on that file. I mean, we use some optimizations there, but in the end, that means every transaction that commits has to do at least one write. And that write then has to be synchronously processed, which means we do the write to the disk, and then the transaction can not report success back to the client until the write has succeeded. And that means we have to synchronously wait on whatever storage device we have. And depending on how fast your storage device is, this can be a long time. If you, for example, just have like an old spinning, rotating disk, you can have like about 140, depending between 110 and 160 writes per second. And that means if you write from a single transaction, from a single client, you'll not have more than 160 transactions per second, which, depending on your workload, might not be a lot. There's Postgres does some tricks. If you do have transactions in several sessions, it will sometimes combine these writes into a single flush to the disk. But still, it means that every transaction has to do at least one write. If you have very large transactions that write a lot, they might have multiple writes, but only the last write that does the commit has to be done synchronously. For that, it's really important to know what the latencies of devices are. Rotational disks are the ones that, the slowest one that you'll usually encounter. A single write will have usually between 8 to 16 milliseconds if it's done synchronously. That's really not particularly fast. The next thing, and one that you'll very frequently encounter, I guess, is that if you have disks that are actually remote to your computer, if, for example, if you use EC2, you'll probably use like EBS, and that means that the storage is actually not on your own hardware. It's like somewhere over network remotely, and that means that you have the network latency, and then you have the latency of the actual storage device. So if you have a network and then use a rotational disk on the other side, that means you have like 1 to 3 milliseconds because of network, and then up to 16 or something milliseconds because of the latency of the storage medium. If you remotely use SSDs, the latency there will be a lot lower. But if you have, for example, have local SSDs and you have a decent SSD, not a very, very cheap one, then you can have latencies around the 0.1 millisecond to a lot lower, depending on how much you pay. If you have a PCIe, like SSD, an enterprise one that can actually sustain a lot of writes, then you can have latencies in the low microseconds. You'll have to pay for that, but other than that, yes. But it's really important to know that one commit essentially means at least one I/O operation. So if you have a workload where you say, I want to do 10,000 writes per second, and all of them needs to be independent transactions, then you will either need to make compromises on your durability, or you will have to say, I need to pay enough for decent storage, which might very well be an acceptable option. But you have to make that trade-off. So what is if you can't afford to pay the price of these expensive writes, of these expensive transactions, because you want to do more writes per second? What Postgres has as a feature is so-called asynchronous commit. You can tell the database that the data is still important and I want to make it durable, but you can say if my computer crashes in the next 1 to 3 seconds and I lose the data, then it's not absolutely disastrous. Which then means that we don't have to do writes all the time. We can combine like up to 3 seconds of transaction commits and do all of them together, which then can mean your writes per second, your transactions per second can be drastically higher. And the parameter for that is called synchronous commit, and then you can set it to off. And that means that transactions will be, if you send a commit to as a client, you will get it back immediately pretty much, and the database will do then the write in the background. And that background write will happen at the moment, at the most after, by default, 3 seconds. So your data loss window is usually smaller than 3 seconds unless you change some other parameters. For a lot of use cases, that's perfectly okay. For example, if you have a workload where you have some writes that are important, for example, let's assume we're doing like a shopping system. You have some writes that are important. If somebody does an order and then you really want to mark that order as durable, because that will make you money and your user will not be very happy if the order got lost. But for example, if you instead have like a user that just clicks randomly around in the shop and goes to a new item, you might want to store which items a user has looked at to later then be able to give recommendations. If you crash, which is unlikely, and then lose like the last 3 seconds of items a user has visited, the user probably won't notice that his recommendations are very slightly worse. So for those kind of writes, you can usually say, these are not that important. For that reason, and that's for a long time was a unique feature of Postgres, you can say per transaction, or per session, or per database, or per user in the database, that I don't need synchronous writes. I don't need synchronous commits. And for that, you just say set synchronous commit equals off, or you can do alter database, set synchronous database name, set synchronous commit equals off, or alter user, or so on. And that means that by default, these users' databases won't perform synchronous writes. And if you need to, you can then set synchronous commit on a per transaction basis, and then the next commit will be done synchronously. And that allows you to do a lot more writes. On my laptop with an SSD, I can do about 4,000 writes, which it has a very good SSD per second if I use synchronous commit on, and I can do about 180,000 writes if I set it to off. And that's with local storage. If you have storage that is remotely over a network, the difference can be a lot larger. You can often see like 3 to 4 orders of magnitude difference. It also not only impacts your performance of writes, if you do a lot of synchronous commits, your reads in other sessions will also potentially get slower because the hardware is busy doing writes and can't do reads. If you have, yeah?
Going back to that slide, what happens if you lose before writing to this?
So yeah, it's very important. Yeah, thanks for reminding me. I forgot about mentioning that. If you crash, that doesn't mean that your database is corrupt or in some in-between state. It will just come out, and potentially the last few seconds of write might be missing, but it will not be otherwise be an inconsistent state that some transactions in the end will have committed, some others haven't. That can't happen. It will just say, we'll just recover up to a point somewhere in the last 3 seconds.
So basically, committed transactions are lost.
Yes, that's why you said synchronous commit equals off. But if another transaction said synchronous commit on and it committed, then that one is guaranteed to be there. So you only set it will only transactions where you marked it as off can be lost.
Is there a session or a user level log too?
Yeah, you can set it per user, per session, per database, per function if you want to, which doesn't really make a lot of sense because it doesn't work, but okay, you can set it per function. Was that what you were asking or something?
I was just wondering, in that case, you would have a separate log per user or per session, whatever would be there, and if you have a crash which happens, would the sessions log be replayed for committed transactions?
No, there's only one log for all the sessions at the same time that are active, all the users, whatever, and then what the difference when synchronous commit is off, the difference is just that the write ahead look will not be flushed at commit time. And if another transaction later then commits and writes something and then commits, and it is marked as synchronous, then it will flush all the previous writes, because otherwise, if it didn't do that, it would get into an inconsistent state after crash recovery. Other question? Yeah?
Does that mean if a small percentage of my writes are synchronously committed, I'll lose most of the performance benefit? Because I still have to flush.
I mean, usually you can do like 10, 20, 30, 50 synchronous writes per second on modern hardware without breaking a sweat. So in that case, it usually is okay, because by default, like the background writer does the writes up to 5 times a second anyway, 5 times per second. So, but if you have like 80% synchronous write and 20% asynchronous writes, you might not see a lot of benefits. So another use case where you might have a requirement for even less durability is if you have like a table where the contents are useful but not super important. For example, if you have a caching table that just caches some metadata you gathered over a more expensive table, if you crash, you can just recompute that data. Or if you have a session table and where you log active sessions of users which you update very frequently. If you crash, the worst thing that will happen is that some users will have to log in again. They'll potentially not be super happy, but it will not cause any permanent damage. For those use cases, you can mark tables as unlogged. And unlogged means that they don't write anything into the write-ahead log, which means that after a crash, the table is completely empty. It will just start out empty. But if you shut down, like normally you say, shut down the database, pgctl shutdown, then it will stop, then the data will be there after start. But if you crash, you'll have lost the data. It also means that the data, if you use Postgres' streaming replication, will not be replicated to the other side, to your replicas, which can be very important for performance. If you have, if you do a couple thousand writes to a session table a second, you don't necessarily need to replicate that because that might be a lot of volume. And the way you do that is you say create unlocked table and then use the normal syntax for create table, and then the table will be unlocked. In newer releases, I think, I'm not sure whether it is since 9.5 or 9.6, I think it's 9.5, you can say auto table name set unlocked or logged, and then it rewrites the table to now be unlocked or logged. That is going from unlocked to logged is a relatively expensive operation because we now have to make sure that all the data for the table is also present on the replica. So we have to basically rewrite the whole table to the write-ahead log, and then we can go from there. If you use trigger-based replication, for example, Londist or Slowney, those will actually just don't notice that the table is unlocked. It will replicate them as normal. This all means that the write overhead of an unlocked table is usually very, very low. Transaction commits still have to write a tiny bit of data into the log that says this transaction committed, this transaction didn't commit, but that's not a whole lot. It doesn't have to do so synchronously. So that's relatively minor overhead. And if you have like very large amounts of writes, it can make sense to use unlocked tables. But you can never rely on the data being present after a crash.
On your previous slide, so is there some, let's say I have a transaction that updates your user table, column 1, right? User 1, column 1 gets updated as a asynchronous transaction. My next transaction is going to update the same row, but a different column, synchronously. Does that guarantee that the first one gets?
Yes.
Okay.
You basically, if transaction commits synchronously, all the previous writes are guaranteed to be there. Otherwise, you would have like random inconsistencies. That would be really bad. You really you get into consistent state as if it were, if after a crash, as if it were happening like a few seconds ago. You don't get into some random state where some transactions previously are committed and some others aren't. So the next,
What's this question? So manually trigger the checkpoint that flush the unlocked?
No, unlocked tables are not written out by checkpoints which happen during normal operation. They're only written out by checkpoints during shutdowns. And that's really important for performance. Imagine you have like your busy session table, which is like 1 terabyte of data, and then you have a bit of configuration metadata that you infrequently update, and every checkpoint would write out 1 terabyte of data. That would not be fun. So it only does so at a regular shutdown. Other than that, they're never flushed to disk unless your shared buffers is not large enough to contain all the data. If your table is larger than memory, then it will still write it to disk, but it will not be necessarily consistent after a crash.
Are they ignored by the background writer?
They're not written out by the background writer, with the exception that if the background writer is making space for writes, then you'll write out a small number, but that only happens if your shared buffers is not large enough to contain the whole database. Yes, unlocked tables are vacuumed as normal. Auto vacuum will process unlocked tables because they can still have bloat, and that would still be bad because your table would get bigger and bigger, and queries would get slower and slower. So the way vacuum works is basically not affected. What's the end of my slot? Can somebody check? Okay. Okay, thanks. There's one more thing that you can do, which is the so-called fsync equals off a parameter, which basically means that Postgres will never ever write anything to disk in a dual manner. That's really, really dangerous. You shouldn't do this. There's a very few exceptions to this. You can do it if you, for example, do regression tests for your application, and you have a Postgres that you immediately will throw away afterwards. That might be okay. But other than that, I would be very, very careful. You really have to know what you're doing. And in many cases, synchronous commit equals off will give you just about the same speed up. So you can do it, but basically afterwards, if you ever had a crash on your hardware, you have to throw the database away and start from again because you don't know whether there's corruption. There's basically no way to detect whether there was corruption. So what is if availability is not enough on a single machine? What is if your durability requirements are higher than a single machine can provide? Because, for example, you're running on cheap hardware, which might be very useful from a financial perspective. Or if you run on spot instances on some cloud provider, you can't be sure that you fail over to a different machine in time. So Postgres has a replication feature built in, which is so-called streaming replication or hot standby, and that allows you to replicate this write-ahead log to a second machine, which will then permanently be in crash recovery. It will permanently replay this write-ahead log, so it will be always updating its state to what happens on the master. That allows you to replicate the state. You can't write to that replica until you promoted it to be the new master. What that allows you to is to have a similar state on the replica than you have on the master. But it's very important to know that by default, this is asynchronous replication. You have no guarantees built into, if you use that just as set up in Postgres, whether how much lag there is between the master and the standby. You have no guarantees, even if the data has been replicated to the master, to the standby, whether the standby has actually applied all the changes. It might have just written the changes into basically a queue of to be applied changes and might still be busy replaying this log. So it might have written the data remotely, but you can't see it yet. And that's basically the case if you have synchronous commit set to off or if you have set it to local. Local means it will do a synchronous commit on the master, but will not guarantee that the write has happened on the standby. And it's really damn fast. Usually, it's very hard to use synchronous commit to local and overload the standby because over the replication mechanism, all the writes are done in a fairly efficient manner, usually in a manner that's more efficient than doing the write via SQL. So in most cases, your standby will be able to keep up on similar hardware between master and standby. There's also really, really few guarantees. What might surprise you is that actually, from the point of a master, if you just look at it, it has actually higher availability, the master alone, if you only look at the master. Because it is asynchronous, because you have no guarantees that data has been replicated to any of the standbys, if all your standbys are down, you can still accept writes. And so that can actually mean that your availability is higher. But if you can't live with the possibility that you lose data, in some transactions, we have a synchronous replication feature since Postgres 9.1. And the way that works is that you can set a parameter, synchronous standby names, and you can set a number of names. And this are basically the names of replicas. And if you configure it like with this list, that means a transaction will only be returned as committed if it has been successfully written to the node A. If node A is not available for within some time frame, then we'll mark that one as dead and we'll go the second one. And so on until you have none left. Your commit will not return to the client until that has succeeded. Since Postgres 9.6, we have an increase of this syntax. You can also say synchronous standby names equals k, and k is a number here. You can say 1, 2, 3, 4. And if you say, for example, 2, that means that the first 2 of those nodes that are alive have to respond, have to successfully receive the write before it is marked as successful, or before it is returned to the client. And the way that you configure that on the standby is that you say primary con info, which is the information where it normally received the data. You basically say application name equals A, then it's marked as node A. If you say B, it's marked as node B, and so on. And you can, again, configure the behavior of whether a transaction is synchronously replicated or not using synchronous commit. The lowest level is off. That is, that is asynchronous commit. Commit, you don't wait for anything. As soon as the statement has been processed internally, it returned to the client as committed. If you have set it to local, then again, that's the synchronous commit behavior, but locally, it will have guaranteed that it's written to disk locally, but it has not guaranteed that it is written to the remote system. The same is if you have set it to on and synchronous standby names has no contents. The next higher consistency level is so-called remote write. That means that the write ahead log has been shipped to the standby, and the standby has written it to disk, but it has not yet called fsync. So it's not guaranteed that if both machines crash at the same time, but the standby then restarts afterwards, and the master dies, you might have lost all the data. But depending on what your situation is, especially if you have like synchronous commit like 3 or something here, that might be perfectly okay, and might be better from whatever storage you have. The next level is that if you have on and synchronous standby names with an actual content, that means that the data has been successfully written to all your synchronous standbys and has been fsynced to disk there. So if the machine crashes and restarts afterwards, you're guaranteed to still have the data. If a commit hits all your servers, obviously that doesn't help at all. And then since 9.6, we have a new level, and that's really important because if I said that with on or the data has remotely been written and fsynced to disk, that does not mean that the database state has been updated. It only means that the write ahead log on the remote side has been written to disk. So what you can have is that the data has been safely written, but if you query the database, the data is not yet there. It's not yet visible, at least. With remote apply, it only returns as committed once the standby or all the standbys in this case have successfully applied the data. And that's very important if you, for example, want to use your standby to process like more expensive queries. A common pattern is to do, for example, have all your writes go to your master and then do writes on the standbys. But if you haven't configured remote apply, you might get into the situation that you don't have the read your own writes guarantee. You have written something and then you go to the standby and you read something, and during testing that looks all good because you don't have a lot of writes, but as soon in load might happen that the visible database state is as of like 3 minutes ago. So that's very important to know, and a lot of people I've seen have gotten this wrong. It's very important to know that sorry? I'll 3 slides ahead or something, then I'll come to it. So synchronous replication really is a very, very useful feature, but it's also really not, it doesn't solve all problems. It's for one, it makes all your commits a lot more expensive because suddenly you don't have to only wait for your local disk, you also have to wait for the data be shipped to the other side, then there it has to also be flushed to disk, and then the message of having been flushed to disk has to go back to the master and then to you. That can drastically increase the latency of a commit message, which then can impact like the throughput you can have on a single session. Postgres tries to optimize that. If you do have a lot of sessions that do synchronous commits at the same time, the writes to the standby will be combined. The feedback from what has been successfully written on the standbys will also be combined. So there's a considerable effort to make that not quite as painful, but it will make your writes more expensive. It will also introduce a lot of more failure modes. Suddenly, if you only have one synchronous replica, and that synchronous replica is down because you restarted it, because it died or something, none of your writes will succeed anymore. Everything will get blocked that is a synchronous commit. That can be a significant problem because suddenly you've increased the number of nodes that can cause a downtime, an effective downtime, by 1. And so you potentially doubled your likelihood of failure. And if you use it has to be written to 3 replicas, you might have quadrupled the likelihood of an outage. So you have to be really careful. One important parameter for that is the so-called val sender timeout. If you have multiple replicas here, if a standby hasn't replied with "I'm doing something," after val sender timeout, it will be marked "You're not a synchronous replica." And if there's no further standbys here, it'll just wait till that becomes up again. But if you have a second standby here, then that will now become the synchronous replica. So you introduce a lot of more complexity. You have to be aware of this. It's also important that you're still not necessarily consistent. You can have the situation that you committed on the master and the commit has not returned to you, but the standby the transaction might already be visible. You can have the reverse situation that the transaction has committed on the master, but unless you use this remote apply mode, the data might not be visible on the standby. So you have to really think more about what kind of consistency you have between the different nodes. And at the moment, there's also no quorum commit. And quorum commit means that if you have this here, if you say 2 here, that means the first 2 synchronous standbys, not that any of 2. That we don't have. That would be a very useful feature because for availability, you sometimes don't care which of the nodes has the data. It's just if it's at least on 3 nodes, I'm good. We don't have that feature at the moment. There's a patch proposed for Postgres 10. It looks like it might get in, so we have a good chance to have that in Postgres 10, but at the moment we don't have it. There's one more durability technique that I want to talk about today, which is a so-called two-phase commit. And that's really only useful if you want to coordinate transactions between multiple systems. Imagine, for example, that you have a shop again, and you want to talk to, for example, your inventory system, which is one database. You want to talk to your billing system, which is another database, and I don't know what else. Then you might need to coordinate transactions between the two, because you don't want to get into a situation where your commit to the billing system was successful, but the commit to the inventory system was not successful, because then the user will get invoiced, but you won't send out the item to him, which makes usually users very unhappy. Or the reverse situations, you might send out the item, but you don't know to bill them, which will make you unhappy. So for some things, it's very useful to be able to have transactions that span several systems. And the usual solution for this is so-called two-phase commit. And what that allows you to have is to split the commit phase into 2 things. You can, let's go through an example. If you, for example, do an insert on database 1, then you do an update on database 2. For example, you say your inventory is the one lower, and on database 3, on another system, this does not have to be a Postgres system. This might also be an Oracle database or whatever. You do something else. If you, in the old world where you don't have two-phase commit, you would have to say here, commit here, or commit here, and that one would be committed at that point. And if then later the commit here fails or the commit here fails, you would get into an inconsistent state. The solution for that is to split the commit phase into 2. You then say prepare transaction, and that you give it a name. And that means after that succeeded, you know this transaction can definitely commit. And it can commit even if that session, if that connection to the client, if that failed, then after you reconnect, you can definitely commit this transaction. That's a guarantee, basically, by the database system. And you do that on all the systems. Then after it succeeded on all of them, you know that your transaction can definitely commit on all of them. And after that, you can do commit prepared. And then these transactions here will be externally visible. Then you can go to the other systems and do that as well. You might say, but what did this trick help me? Because I still did the commit individually. but it allows you to, if one of the databases crashes, if your program crashed, you can afterwards go and redo all the commits. And if the commit prepared succeeded on all of them, you just redo as long as it succeeded everywhere, and then you're good. There's some significant complexity to getting this right, because somewhere you need to keep track which transactions are actually in progress. But there you usually want something called a transaction manager, where you register which transactions are at the moment in progress across all the systems, and then that one takes care of actually committing them. There's integrations in, like in the Java world, which there's a integration into where you can register transaction managers and has a lot of that integration. If you use other platforms, you might have to do some of that yourself. But it is a very useful tool, and I don't want to go into detail when and how to use it exactly, but it might give you something to Google or something for if you are in the situation that you need this. Okay, I think, oh yeah, the only thing that if you had a failure in one of them, you can instead of commit saying rollback prepared, but that's kind of obvious, I guess. So, any questions?
I have a question about one of your first slides about the shared buffer relation between shared buffer and the checkpoint.
Mm-hmm.
Checkpoint size. If your checkpoint size is very, very huge than shared buffer, and if all of the pages on the shared buffer are dirty,
Mm-hmm.
like what happens when you try to
The checkpoint will only write out the pages that are dirty. It doesn't have to do anything else. It doesn't have to do any new write-ahead logging or something. So it will just go through there sequentially and write it out to disk.
Yeah, but my question is like, if you have, for example, 1 GB of the shared buffer, and let's assume that all of the pages are dirty,
Mm-hmm.
and your checkpoint size is 10 GB. So,
But those are different sizes. So so what you're talking about is basically the size between those. This here is the size in log segments.
okay.
So that will just means the checkpoint happens after 10 gigabytes, at most 10 gigabytes here have been written. But that has no influence over the shared buffer size. If the shared buffers is full, then we'll just write out the data during the select, during the insert, during the whatever.
So I share a concern with fsync off.
Mm-hmm.
Is it full page right also equally dangerous with off?
Yes, full page writes off you should really not do unless you have a synchronous replication setup and you always fail over after every single crash. I think that's the only case where you can use where full page writes equals off. There's some tricks if you recompile Postgres with a smaller page size and the page size is the same as the hardware page size and the blah, 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 blah. But yeah, I've just not seen it happen as often. I've seen a lot of people use fsync off. I've very few people seen in production use full page writes equals off.
Does every transaction have like a transaction ID?
Yes.
Because in case of replication, if your network goes down, your connection to the your downstream replicator goes down, when the connection comes back, do they actually exchange like what was the last transaction ID?
No. It would be a very useful feature, and people have been working on adding that feature, but at the moment it is not present. You can do it with, if you use Twophase commit, you can do that, because then your ID just becomes the string you give the name, you give the transaction. But without that, at the moment, it's not possible, unfortunately.
So currently, what happens when you have a network break and then both sides are able to talk to each other? How do they sync up saying that?
You mean with streaming replication or with, streaming replication, basically the way it doesn't use the transaction IDs at all. It basically, everything in this write-ahead log has a byte an offset from the start. It's a 64-bit number, and that's just saying at position so-and-so, and the standby knows how far has it received data and how far has it replayed data, and then it can just ask the master, give me everything from this byte position again. So I thought you meant like what if a client sent a commit and after sending the commit the connection breaks, then you don't know whether the server has committed to the transaction or not. I thought that was what you were referring to.
I missed how log tables get persistent.
Well, they don't.
at all. So
No.
what's the difference between temporary tables?
So unlocked tables are shared between all sessions. If you can, your application does not necessarily need to know that is an unlocked table, except for you need to know what durability it is, but it does behave the same way as a normal table. If one session writes something, the other session can see this. And it actually is persisted if you shut down in a regular manner. Like if you say, please database shut down, I'm giving you time to write all your data, and then you restart, then it's there. But any other situation, it's not there.
So it's either all or nothing? It cannot be corrupted?
Yes. I mean, unless you see an empty table as corruption.
You don't see deployed battery pack storage. So if you have battery in your storage system, you can actually safely have synchronous commit to open.
No, it's not true. Synchronous commit only writes to the kernel's page cache, and that does not necessarily write to data. So that there's no guarantee there. And even some people argue that you can set full page writes equals off with a battery-backed cache, but that's not true, because by default the Postgres val page size is 8 kilobyte, and the operating system page size is 8 kilobyte, and which means that the writes to the storage are also done usually in granularities of 4 kilobyte, so you can have torn pages exactly at the 4 kilobyte mark. Okay, cool. Thanks.